this question again is unresolved. Majorana Fermions in relativistic theory can have a mass, so not having a mass doesn't get rid of them. The question is whether pairs of Majoranas, pure pairs of neutrinos, can sort of annihilate themselves, leading to a double beta decay, but that hasn't been seen. My talk today will be mostly focusing on whether one can find Majorana Fermions as emergent particles in solid-state systems. So just to step back, let me discuss the story of Dirac fermions in condensed matter systems. Of course, semiconductors are made up of regular electrons, which are regular fermions, and they're just particles. However, the many-body state of a semiconductor has fermionic states which are either empty, which are described by the conduction band, or filled states, which are described by the valence bands. Excitations of an empty state are in the form of creation of an electron, and these are particle-like operators. And on the other hand, for the filled states, one can only, the excitation is to remove a particle, and that's a hole-like excitation. So that's the analog of the Dirac equation, of the Dirac particle-hole pair in regular semiconductor physics. I'll note that in the particle and hole operators are related to each other by complex conjugation. So if one were to have a fermion which is its own antiparticle, one would expect its second quantized representation to be in terms of a fermionic operator, which is Hermitian or self-adjoint. However, as you noted, a single regular fermionic state is either empty or filled, so it has a single quantum state. However, to construct, if one has one one needs to take a pair of Majorana fermions to form a complex fermion, which would have a single quantum state. Therefore, in some sense, Majorana fermions are sort of half of a quantum state. Now, let me try to explain this in a little more detail, because this is one of the hallmarks of Majorana fermions. Let's say we have a system which has a localized Majorana fermion, a pair of localized Majorana fermion operators, and they always come in pairs. So the Majorana operators are gamma 1 and gamma 2. To consider this quantum state of this many-body system, one really has to consider the pair of gamma 1 and gamma 2 into a regular complex fermionic operator. This complex fermionic operator is not, is actually just strictly delocalized between gamma 1 and gamma 2. And then one can talk about the state of this complex fermionic operator as being, it's a fermionic level as being filled, which is a quasi-particle state, or empty, which is the vacuum state. Therefore, this pair of Majorana fermions sort of has a hopefully robust and fundamentally delocalized quantum state. Now let me describe what is the most fascinating property of these Majorana fermions is this idea that they have non-abelian statistics. So let me try and explain what precisely this statement means. So let's say we have a prototypical two-dimensional system. Let's say a chiral P-wave superconductor. The details of this is not going to be important for this discussion. And then let's say one has vortices in this chiral P-wave superconductor, and it has been shown that these vortices trap these localized Majorana fermion operators. Now one can ask, what is the ground state wave function of this system of P-wave superconductor with vortices? That ground state wave function, if you call it psi, would require the specification of the position of each of the vortexes. These are the coordinates, R1, R2, Ri, etc. But in addition, that would have, if one stopped at the position of the vortices, that would be like an S-wave superconductor. But for systems with Majorana fermions, one also needs to specify this index J, which specifies whether each pair of vortices, or the Majoranas in each of these pairs of vortices, are in the quasi-particle or vacuum state. So there's actually these indices J are a set of n two-state systems, which are quasi-particle or 1 or 0, so they're sort of like a 2 to the n dimensional space describing the ground state of this PO superconductor. What is interesting is now if one were to consider a state where all the pairs of vortices are in the vacuum state, so each, let's say this pair and this pair of Majoranas, they are in a vacuum state, and then one took one of the Majoranas from one of the pairs and the other Majorana from the other pair and exchanged them. One can show that that fundamentally scrambles this large Hilbert space, and this is described in terms of a transformation, which is a matrix, in terms of a matrix transformation of this ground state wave function. And typically, since the ground state wave function is being transformed by a matrix, these transformations are non-abelian. In contrast, for regular fermions, one would have just picked up a phase if the Majorana fermions were just regular fermions. So basically this is sort of a dream kind of interesting system where Majorana fermions not only have a large ground state degeneracy which is robust, but they could be manipulated through these topological operations. The story of Majorana fermions has been discussed theoretically, and non-abelian statistics has been discussed for a while, and that was significantly before I was involved in this kind of work. The motivation for the work that I'll be talking about is trying to understand simpler systems which would have non-abelian statistics, and hopefully that would make them more experimentally realistic. Historically, the first system which was shown or proposed in a very precise way to have this non-abelian statistics and Majorana fermions was the mu equals 5/2 fractional quantum Hall state. This was work by Moore and Reed, who wrote down the Pfaffian ground state wave function for the system and showed that there would be Majorana fermions. However, the fractional quantum Hall system is a very strongly interacting system and has not been solved, and one really doesn't know if there's a if there's ground state is the Pfaffian wave function. And so this question still remains open and is being investigated experimentally. The next observation was that the simplification was done by Reed and Green, who observed that the spinless chiral PO superconductor, the mean for ground state for that system was the same Pfaffian wave function as the Moore-Reed state, and therefore it should also have Majorana fermions. This is a simpler, essentially non-interacting system that had been worked on by Volovic and others. Unfortunately, in nature, there aren't many even chiral P wave spin superconductors for spinless, and strontium glutamate is the closest candidate, and that still a strongly interacting system and highly debated. So the next, what got me excited about this field was the discovery of Fu and Kane that the interface of an S-wave, a regular topological insulator that was the subject of the morning session, with an S-wave superconductor, both of which can be described by essentially first mean field Hamiltonians, would support a Majorana fermions, and this to me was a very interesting breakthrough. The question that we asked was whether the topological character of the topological insulator was crucial for realizing Majorana fermions here, or was it really just a spin-orbit coupling? And to our somewhat surprise, we found that actually it's really spin-orbit coupling that's the crucial ingredient, and a fairly generic class of systems which have spin-orbit coupling, Zeeman splitting, and S-wave superconductivity would support Majorana fermions. This discovery was followed by a whole list of proposals, so that now that there are really a lot of promising systems where Majorana fermions might possibly be seen. So now the question one asks is, what is this connection, how does one simply see the connection between superconductors and Majorana fermions? To see this, note that the superconductors is really a condensate of, as a regular S-wave superconductor is in some sense just a condensate of Cooper pairs, loosely speaking. And a semiconductor, as I mentioned, has electron and hole-like or even a metal or regular Fermi liquid has electron and hole-like excitations. Well, now if one brings a semiconductor next to a superconductor, what can happen is that an electron can scatter coherently off the superconductor and get reflected as a whole. This is the process of the well-known process of Andreev reflection. This process suggests that the quasi-particle excitations of the of the semiconductor next to a superconductor would be a coherent superposition of electrons and holes. And now to make this d-dagger self-adjoint or Hermitian, all one has to do, and therefore a Majorana fermion, all one has to do is somehow arrange for this this coefficient u to be equal to v star, and one would have a Majorana fermion. And since d and d-dagger are really part creation and annihilation operators of the same state, this suggests that this must have exactly zero energy.
And also you have the spins the same.
Yes, so that's actually a crucial point. So actually note that I have kind of not specified the spin index, and that's where spin orbit coupling will become crucial to make sure that the system doesn't really have a spin degeneracy. And that's also at the root of why we needed a spinless superconductor in some sense, or a single Fermi surface. Okay, but I'll come back to this point. That's a very crucial point. That last discussion made it sound that Majorana fermion should happen whenever there is a bubble-above particle. You can always somehow manage to make u equals v star. But it turns out that's actually not that simple. And the way to see this is the following. Let's say so if one has a superconductor which is gapped in the bulk, the only way to get a low energy excitation, the simplest way, is to have some kind of a vortex or a defect which would have a bunch of low energy excitations. And typically, since these excitations are being labeled by the operators d dagger and d, excuse me. So they have a set of excitations, but since this is a confined system, one would expect the excitations to be discrete. And moreover, because the operators come in like particle hole pairs, like these states with energy E corresponding to d dagger and states with energy minus E corresponding to d, the operator d, the spectrum would have a fundamental particle hole symmetry. And if one has a zero energy parked right in the middle, one can see that by continuously deforming the Hamiltonian, there's no way to get rid of this zero energy state because the states all move in a symmetric fashion. The only way to get rid of it is to somehow have a continuum of states come into the vortex, and that sort of ruins the counting, and then one can get rid of the equals zero state. And this continuum of gapless states can only happen if the bulk gap closes, and that's the hallmark of a topological phase. So basically, to summarize, a Majorana fermion, the occurrence of a Majorana fermion in a vortex is just like the edge state of a topological phase. It signals the existence of a topological phase. And now, before going into the details of our system in a little bit, I should point out that this picture of the semiconductor next to a superconductor with the Cooper pair condensate is precisely what is used in our calculations. So if one considers a semiconductor next to a gap superconductor, since the semiconductor is doped and has gapless excitations, one can integrate out the superconductor. And what that does, by considering a process where the gapless quasi-particle from the semiconductor tunnels into the superconductor, propagates in the superconductor, picks up an anomalous part, which is the pairing part, so it's a side-dagger term, and then it hops back. And the effective self-energy induced in the semiconductor is like a superconducting pairing term. So, given this idea, we consider a geometry which is a semiconductor, that's a spin-orbit coupled semiconductor slab, that's described by usual quadratic parabolic dispersion for the electron dope case, with a Rashba spin-orbit coupling, and then we add a superconductor next to it, and this by integrating out the superconductor, can be shown to introduce this pairing term, and then in addition, one needs a magnetic insulator. This is actually a point I'll come back to induce a Zeeman term, and I'll explain in the next slide why one needs the Zeeman term. And the result, and then one can put a vortex in the superconductor, solve the Bogoliubov-Dejean equations analytically, and show that there is indeed a Majorana fermion zero mode. I won't go into the details of that solution, but let me come back to this point of the role of spin polarization and spin-orbit coupling. And this is seen most directly by considering the band structure of just a regular semiconductor. Forget it in the spin-orbit coupling of an electron-doped semiconductor is just a parabola, but generically it has a spin degeneracy. However, if we apply a magnetic, to get Majorana fermions, we sort of want to get rid of this extra spin degeneracy. So we think of applying a Zeeman potential that leaves the spin up Fermi surface and with the spin downs being gapped. And now if the chemical potential is tuned to be in the spin up Fermi surface region, one sort of has a spin non-degenerate Fermi surface. But now if one wants to put an S-phase superconductor in here, one's in trouble because an S-phase superconductor wants to pair spin up with spin down. It can't pair spin up with spin down. So typically this is in the so-called Chandrasekhar-Klockstone limit where there's no pair. This is just a gapless phase. However, if one introduces spin orbit coupling, that causes the spins at the Fermi surface to cant a little bit, and now there's a nice projection into the singlet channel of this pair of Fermi surfaces. However, if one looks at the effective superconductivity induced in this single Fermi surface, it's still in the band projective sense is effectively P-wave, and that's what's responsible for the Majorana-ness. Of course, this is an approximate treatment, and one can include both bands and do the full calculation of the zero modes, the mean variant, and it all works out. Incidentally, the semiconductor recent developments have led to the realization of spin-orbit coupling in cold atomic systems as well. This is the work of Ian Spearman in Maryland. And this leads to the possibility that given that one also knows how to get Zeeman coupling and S-phase superconductivity in cold Fermi gases, that cold atomic gases might also be a candidate for realizing the same kind of physics. And there has been a fair bit of work in this direction as well. Now, the solutions of, the point of view of topological superconductor of the solution, or equivalently the solution in terms of Bogoliubov-Bejan equations, predicts actually a lot of geometries in this semiconductor systems which would have Majorana-like excitations. For example, if one didn't have a vortex and just looked at the edge of this of the semiconductor superconductor system, one would find that there's a chiral Majorana edge mode going around the system. Moreover, if one just considered a pi Josephson junction, one would find a non-chiral Majorana mode going through this junction. A magnetic domain wall in the system would produce a chiral Dirac kind of mode similar to this. So both of these are similar to topological insulator superconductor systems. But what is most exciting for us is actually if one just solves the Bogoliubov-Bejan equations in one lower dimension, that is, takes a one-dimensional semiconductor, one doesn't even need a vortex to get Majorana fermions, and just the end of the system would have these zero modes, provided the Zeeman potential Vz, the pairing potential delta, and the chemical potential mu satisfy this constraint. So actually, the superconducting proximity effect in an indium arsenide nano, so the typical spin orbit coupled nanowire such as indium arsenide has also already been observed more than 5 years ago at a group in the Cohenhoven group in Delft. So for me, this is one of the most promising places to start looking for Majorana fermions, well, among others, of course. So I'll describe this geometry in a little bit of detail. So the specific system is to consider an indium arsenide nanowire, which has spin orbit coupling, on top of an S-phase superconductor, let's say niobium, and the Zeeman splitting can be induced by an in-plane magnetic field, which for thin films and thin nanowires would not have a strong orbital effect. And the prediction is that when the magnetic field is sufficiently strong so that it's above this threshold value of squared delta squared plus mu square, one would find a zero mode. And it's only in that case one would find a zero mode. And the zero mode could be looked for by a scanning tunneling microscope probe in the end. More specifically, let's discuss what exactly one would see if one were to take a scanning tunneling microscope or some other form of tunnel probe around this nanowire system. So the first thing one would do is start by probing the middle of the nanowire, which I'll call the bulk. So in that case, at zero magnetic field, one would find a regular S-wave gap, which is which for niobium would come out to be about, I don't know, half a millieV. And as one raises the Zeeman field, one would find that this gap gets uniformly suppressed. And this is the familiar suppression of superconductivity by magnetic fields. Or this is sort of the Pauli depairing, and this is the Pauli depairing limit. And then after that, without spin-orbit coupling, one would expect that to be the end of the story. However, with the presence of spin-orbit coupling, the gap actually comes back up again, and one has a gap now which is in the so-called topological phase, which is proportional to the spin-orbit coupling. Now, instead, if one, so that suggests that, well, observing this kind of a transition would itself show that at least something happened in the nanowire. To look for the Majorana Fermions, of course, one has to look at the ends. So if one looks at the ends of the wire and plots the tunneling conductance as a function of bias voltage for a variety of Zeeman splittings, at 0 Zeeman, one would see that basically there's no conductance in a large range of the bias voltage from over 0.5 millieV. And then, as one increases the Zeeman voltage, one would see a pair of this Van Hoff singularities at the edge of the tunneling spectra start to close in. And beyond the critical value of Zeeman, there would be a peak, a zero bias peak in the middle, and which which would persist at larger values of Zeeman as the sideband separated out again. Of course, and now what is more interesting is actually that this peak is not only is it just magnetic field dependent, it actually also has an exact, as in the low temperature limit and conductance of 2 squared over h, which would also be a very interesting scenario of having an end mode with a quantized conductance. I should also point out that it's not necessary, one might be worried that one needs a very small chemical potential for this system to work. However, for nanowires, one can work in a multi-band regime where several bands are occupied, and this chemical potential mu that I mentioned really refers to the chemical potential relative to the bottom of some mini-band in a nanowire. Another signature for this kind of PA-type topological superconductivity was pointed out by Kitaev and the Ponce and Gupta here and Yakovenko and others, is the fractional Josephson effect. Now, for regular S-phase superconductors, if one tries to make a tunnel junction between two superconductors, if there are no low-energy quasi-particle states, the only way to get a current is for a Cooper pair to break apart and first tunnel as one electron and the second electron tunnels after it. This leads to 2 factors of T e to the I phi over 2, so that the total tunneling amplitude is proportional to the flux, and the resulting current is then 2 pi periodic in the superconducting phase. But if one has these kinds of low-lying Majorana type excitations, or actually maybe even more Majorana excitations, the low energy effect of a tunneling term is not to tunnel this. Is not just to tunnel a Cooper pair, but just to hybridize this pair of low energy excitations. This effect comes with just 1 power of the tunneling, so it's a sine phi over 2, and this leads to a very interesting effect that the supercurrent is not just periodic in the superconducting flux quantum, but it's 4 pi periodic in the superconducting flux quantum, which is counterintuitive when one thinks of the superconducting phase as specifying the state of the system. And this can be argued has been argued by Kitaev to be related to the topological character of the topological quasi-particle states of this pair of Majorana Fermions. Yes?
Seems to be a first order effect.
Yes.
Make it bigger compared to the standard Josephson.
That's true. It is. It's well, okay. I should say no. In the small tunneling limit, that's definitely true. However, what really limits the Josephson current is the hopping is actually typically even almost larger than the pairing amplitude. So the Josephson current gets related really by the bulk superconducting pairing gap. And so in that sense, the qualitative number usually is the same order of magnitude. Okay. Now, so there have been, so these proposals have been around for a while, and they're actually fairly they have inspired a fair amount of experimental efforts, particularly in the Delft group of Leo Kogenhoven, also John Martinez and Santa Barbara and others. But there seem to be some possible, while experimental progress is being made, since we're really hoping to see this Majorana fermion in the system, we decided to try and address some of the potential experimental challenges, which could generically occur in the system. And one of these challenges is the fact that, the proposal involves putting the semiconductor directly on top of the superconductors, and that one could imagine that would make any level of control of the chemical potential fairly difficult. And the other difficulty is sort of specific to the semiconductor topological systems, which require the breaking of time reversal symmetry. And because of that, one doesn't have an Anderson's theorem protecting the topological gap. And this was pointed out first by Andrew Potter and Patrick Liu, and then we have worked on making more refined estimates of how much of a challenge this really is. However, on the other hand, we have all come up with proposals which require, in some sense, more microfabrication, but at a level that has already been done by people like the Delft group of considering quantum dot superconductor arrays, where each quantum dot traps a single, with a magnetic field and a gate, traps a single spin polarized electron in each dot. And this creates a system which is similar to the Kitaev chain, and the superconductors allow both tunneling and cross-Andreev reflection. So this leads to a direct analog of the Kitaev chain, which can be shown to be more disorder robust. And the Kitaev chain also provides a very beautiful description of how the Majorana fermions emerge. The idea is to consider the fermion operator in each quantum dot as really a complex superposition of a pair of Majorana operators, gamma 1 left and gamma 1 right, and so on. And the coupling of tunneling and cross-Andreev reflection strongly couples just these pairs of Majorana fermions, so gamma 1 right and gamma 2 left, gamma 2 right and gamma 3 left, and so on. And once these are strongly coupled, they're split into complex fermions in a dimerized fashion, so that only the last Majorana fermions are left at the ends, and this could be studied by tunneling. So now let me change gears a little bit and ask some somewhat more abstract questions about the origin of Majorana fermions. All these studies of Majorana fermions were done at the mean field level, where the Majorana fermion, the superconductivity was treated by BCS theory. And as a result, the definition of the Majorana fermion, which is the superposition of electron and hole, is one that breaks superconductive number conservation in a fundamental way. So that doesn't make any sense. Because we know that the physical system actually conserves number. Moreover, even the definition of topological degeneracy was in terms of saying that the degeneracy associated with Majorana fermions is a degeneracy between even and odd number states of the wire, which again doesn't make much sense in a number conserving system. And in fact, this was taken advantage of by Liang Fu in one of his papers, where he showed that a gate voltage could be used to generate and charging energy could be used to generate teleportation between Majorana fermions, showing that really this charge quantization is quite an important fact in these, plays an important role. So one can ask, it's tempting to ask the question whether one can define Majorana fermions and topological degeneracy outside the confines of mean field BCS theory in somewhat more symmetry-based way. And number conserving way. So again, this was the study, one such system that one can study this was motivated by the spin orbit coupled wires. So if one looks at, zooms out and takes a cartoon view of the multi-channel wire, so a nanowire, one has a series of parabolic dispersions. These are spin split by the Zeeman splitting, and as before, the S-wave superconductivity produces a P-wave type pairing because of spin orbit coupling. So in some sense, one can think of this as basically just multi-channel fermions with a weak attractive interaction, and coupled by a weak attractive interaction. However, one notices at this point a very crucial fact that one needs at least more than one channel, because the single channel problem has been solved over and over again, and one knows that the answer is just a gapless Leffinger liquid. So how does one generate to generate a quasi-particle gap in the bulk of the wire, one needs a few channels. So to deal with the attractive, weak attractive interactions, one can, the systematic formalism in 1D is to use bosonization. But the nice thing is that the operators in bosonization have a nice physical interpretation. The bosonized representation of the fermion have a nice physical interpretation. So the theta and phi, so the bosonic fields theta and phi represent. So phi represents the charge density of the fermions, and theta represents some kind of superconducting phase, and these are in some sense canonically conjugate. Now most of the attractive interactions that one can write down for renormalization group sense, and this leads to a pinning of the differences in the phase, so that the phase variable is now pinned to an integer multiple of pi, the integer being 0 or 1, and a global superconducting phase. So this kind of a 0-1 pinning of the superconducting phase suggests kind of an Ising. I should actually be a little more careful. This is really half the superconducting phase. So the true superconducting phase is just an integer multiple of 2 pi. But this suggests that there is some kind of an Ising order associated with each of the channels, even though there is no longer a superconducting order. And this Ising order reminds us of the traditional context where Majorana fermions occurred in solid-state systems, which was in the transverse field Ising model. So if the transverse field Ising model is just the regular Ising model with spins coupled by a ferromagnetic interaction, and together with a magnetic field which does not respect the Ising symmetry. And this is a quantum system, and can be solved exactly by introducing domain wall excitations, which are really and making a Jordan-Wigner transformation. This leads to this domain walls behaving like Majorana fermions. And now this Jordan-Wigner transformation has done something nice. It really taken this topological degeneracy of Majorana fermions and mapped it to this Ising degeneracy. So, but it should be kept in mind that this doesn't mean that the Majorana fermion is just another guise of the Ising model, because what's really crucial here is the non-local transformation, which takes the symmetry-broken degeneracy to topological degeneracy. However, our system of the multi-channel superconductor is somewhat more complicated, and one needs to take care of that with a more sophisticated Schultz-Mattis-like treatment, which shows the topological order only emerges in an odd-channel wire. But this formalism is a natural treatment of Majorana fermions and the phonon modes. And I'll just rush through this quickly. One can then ask, in what sense is the system topologically degenerate? So to see this, one can add a local potential explicitly into the system and try to see if this degeneracy is topologically protected. One finds actually that instead of being exponential, the degeneracy protection is actually a large power law where the power is determined by the proportional to the number of channels of the wire. So in conclusion, the semiconductor superconductor systems are a promising set of systems where experimentalists are already looking for topological superconductivity. However, there are numerous experimental challenges which hopefully will be addressed. the combination of theory and experiment. On the more theoretical front, one can use Boson's. These models also motivate Bosonized models, which allow us to think of get a nicer understanding of topological degeneracy in these systems. And finally, my hope is that in future, this kind of attempts will sort of lead to a merger of the treatment of quasi-particle spins and the field of superconducting qubits. Thank you for your attention.
Surface.
Yes.
You don't really need the topological nature of the substrate. You need the spin orbit scattering there.
Yeah, that's the point, yes.
So do you think the same thing could be achieved by, for example, in a quantum Hall state of a two-dimensional system when you couple that to a superconductor?
That's actually an excellent question, and you need some kind of spin polarization. So the proposal was to use a half metallic kind of states, or even quantum Hall edge states. But the problem with quantum Hall edge states is usually that they come with a large magnetic field, so it's really a technical issue. So if you avoid that, then that's also a viable candidate. Right.
So is there a wild Fermion type realization, without what Ashwin talked about?
That's actually a really interesting question. So there is a wild Fermion analog of this, and we actually put a paper on the archive talking about this. So, but it's well, okay, it's sorry. No, so what it is that if you take a ferromagnetic superconductor, then you yes, and then you have you get a condition similar to similar to this topological condition, but then I guess I don't want to get into the details, but the point is that in the Bogolubov-Dejean spectrum, you get a pair of wire modes, and they come with their own Fermi arcs, and it's not actually spin degenerate because of the ferromagneticness of the superconductor. But I guess conceptually it's very similar to Ashwin's work.
On the last slide,
yes.
This large number of superconducting channels.
Yes.
What it was about?
That's actually a very good question. And so this is actually okay. So for the practical point of view, for the proximity-induced superconductor system, so the nanowire on a superconductor, that's not so much of a problem because the superconductor is really a two-dimensional superconductor, so in some sense it has a very large number of channels. But in reality, this description was not really meant for, we didn't have a Coulomb interaction, for example. This was more for a cold atomic system, where one really has these local interactions, and there actually this large number of channels can be a concern. And there the solution is probably to couple a large number of these wires, or have
You mean thick wire or something?
yeah, for example, a thick wire, or have many wires together, coupled together. Yes.
So let's thank Jaideep again.